Hi, and welcome to this course on the fundamentals of project design for data science and machine learning projects. Our learning objectives for this presentation will be first, identifying a business objective because simply our data science project needs to be straightforward. Second, determining a deliverable, in other words, how will a model be used? Number three, the choice of classification metric, which reflects to the need to measure success effectively. Four, establishing data infrastructure, in other words, the importance of the data engineering side of things. And number five, the life cycle of a data science project, an in-depth look of how a project gets executed. We've spent a lot of time in this bootcamp discussing how to model. We've learned how to code in Python and SQL, how to visualize and analyze data, and how to train and evaluate a variety of models. However, we've been working with datasets that have already been prepared and focused on a goal that's been given to us. For a data science project to succeed, we need to choose the right project to pursue in the first place. An innovative idea is nothing more than an idea if we don't have the data to support it. A model that doesn't outperform current analyst estimates does not add value. Finally, a predictive model, which our business analysts cannot use, is not helpful regardless of its mathematical value. With that said, many practices discussed in this presentation are somewhat vague. Unlike with code, it is not easy to provide a step-by-step guide for designing a data science project, but we can certainly outline the essential aspects of a project's life cycle. Each project depends on the domain and is different from the others. Therefore, we'll do our best to go over the critical details to keep in mind. That should help as a guideline and must be used in tandem with a data scientist's most vital toolset, intuition and domain knowledge. As already discussed, most real-world data science problems are not as straightforward as those found on Kaggle. Sometimes we receive a goal from a stakeholder without a well-defined dataset or metrics. Other times, we've identified a problem on our own that could be solved using data. In both cases, it is vital to identify the business objective. Here are a few examples. Improve demand forecasting, increase revenue, reduce customer churn, increase email click rates, predict the likelihood of returns. Let's say that we've been asked to predict the likelihood of a return of an item bought. When working with a business objective, it's essential to have in mind the why. Are we trying to identify customers who prefer a different style to improve a recommendation system? Or are we trying to identify styles and fits that are losing popularity? While a business objective will form the core of a project, it is clear that there is a lot of nuance and decision-making involved in tackling the problem at hand. Before we start looking at the data, we ought to think about how a model will be used. It doesn't matter how much data we have if the model sits in the cloud unused. Here are a few questions that should be answered. Who will use this model? As in, is it the data science team or a business analyst with no coding experience? How will the model be used? For example, will an analyst use a prediction directly or will it be used as a tool to improve analytical work? What are the current approaches to this problem? Meaning, do we already have a forecasting tool? Take the business objective of predicting return likelihoods. Is a model that predicts the probability of each purchase to be returned helpful? Not likely. However, in training a predictive model, we can understand the qualities of clothes that lead to returns. How common are returns of accessories vs jeans vs shirts? If we can understand the commonalities amongst clothes, maybe we'll discover commonalities between customers. We might be able to recommend clothes to customers based on the likelihood that these clothes won't be returned. In the world of Kaggle, we would have been given a dataset and then tasked to find the best predictive model. However, this skips the most challenging part of a data science project, the flexibility to try various approaches to find the best solution to a real-world business objective that drives value. Now that we've decided on a deliverable, we need to choose a metric that we will use to measure success. It is a crucial component of any project as we'll need to pick the model that performs the best. However, this is also a vital step in communicating with our stakeholders. Our stakeholders will struggle to understand many of the model's fine details and different implementations. Therefore, it is essential to have an agreed upon metric to help us explain our progress succinctly. After data collection and exploratory data analysis, the first step is to provide a baseline metric. It could be one of the baseline metrics we've discussed in previous lessons or the metric for the current performance. That is, of course, if analysts are providing the forecasts. Once we have agreed on a baseline metric that our stakeholders can understand, it becomes much easier to communicate our progress and the success of our final model. This section is about our data and the question of whether or not we have the required data stored somewhere. This step takes place right before EDA. When building a possible dataset, there is usually an interplay between database and dataset exploration. We need access to our targets, but besides our targets, we need to make sure we have enough of the following. First, scope. Does a dataset have enough data points and does it capture the real world? An example of a potential flow is the date parameter, as some databases are younger than we'd like and don't capture enough temporal data. Another example would be if our database only had product returns that were filled out online but did not capture in-store returns. Just as class imbalance causes issues with a dataset, a lack of scope can cause problems with a dataset as well. Second, rich feature set. It does not help to build a model if we don't have enough features. We need to dig through the database for tables to connect to and gauge how useful they'd be. Ideally, we would have done some preliminary work before throwing significant resources at the project. We both need a variety of potential features alongside the ability to tie tables together. And last, available resources. In some cases, we might store different features in two locations. Even if we could gather the data into a clean dataset and get good results, the data pool would be very costly when we put the model into production. We would need additional support and resources to deploy this model, which might not make the project worth it. If we run the model only once a month, this won't be as big of a deal. The model might require GPU support for more complicated models, such as computer vision or NLP. When data wrangling, it is essential to consider that once the model is in production, we will require resources proportionate to the ones we've put into building and transforming the dataset. So far, we've examined basic project design concepts and ideas that will help us manage a data science or machine learning project. Now let's discuss the project's lifecycle and execution in more depth. Machine learning and data science projects are highly iterative. As you progress through the lifecycle, you'll find yourself iterating on a section until reaching a satisfactory level of performance, then proceeding forward to the next task, which may be circling back to an even earlier step. Moreover, a project isn't complete after you ship the first version. You get feedback from real-world interactions and redefine the goals for the next iteration of deployment. It may be tempting to skip this section and dive right into just see what the model can do. Don't skip this section. All too often, you'll end up wasting time by delaying discussions surrounding the project goals and model evaluation criteria. Everyone should be working toward a common goal from the start of the project. It's worth noting that defining the model task is not always straightforward. There's often many different approaches you can take towards solving a problem, and it's not always immediately evident which is optimal. If your problem is vague and the modeling is not clear, you need to define the project's requirements before proceeding. Ideally, a project has high impact and high visibility. Mental models for evaluating project impact would be to look for places where cheap prediction drives large value, or look for complicated rule-based software where we can learn rules instead of programming them. Also, some useful questions to ask when determining the feasibility of a project are the cost of data acquisition, the cost of wrong predictions, the availability of good published work about similar projects, and the computational resources available both for training and inference. Also, when specifying project requirements, it's best to establish a single value optimization metric for the project. For example, optimize for accuracy, prediction latency under 10 milliseconds, model requires no more than 1 GB of memory, etc. The optimization metric may be a weighted sum of many things which we care about. Revisit this metric as performance improves. Last, a well-organized machine learning codebase should modularize data processing, model definition, model training, and experiment management. In this example codebase, you can see the modularized structure we just discussed. Data provides a place to store raw and process data for your project. Docker is a place to specify one or many Docker files for the project. App.py exposes the model through a REST client for predictions. Models defines a collection of machine learning models for the task, unified by a common API defined in base.py. Datasets.py manages construction of the dataset. Experiment.py manages the experiment process of evaluating multiple models and ideas. Train.py defines the actual training loop for the model. Data is power. When the problem is clear and an appropriate machine learning approach is established, it's time to collect data. Data can come from multiple sources. You might have an internal database that can be queried for relevant data. You can ask data engineers to extract the data for you or use existing services like Amazon Mechanical Turk, or perhaps do it yourself. Others receive data from the clients. Another option to consider is buying data from third-party providers. There are also open-source datasets. Your goal is to collect as much relevant data as you can. Later in the life cycle, you'll go through the data preparation step, which might remarkably reduce the number of samples in your dataset. If you haven't collected enough, you have two alternative options to go with. Data augmentation, which will introduce extra variations to the existing dataset, making the model better at generalization. Synthetic datasets, on the other hand, are new samples that can be used as inputs to your model, for example, data that can be generated with GANs. Collected data is messy. There are many problems that machine learning engineers face when dealing with raw data. Here are the most common issues. Relevant data should be filtered. Irrelevant data should be cleaned up. Noise, delusive, and erroneous samples should be identified and removed. Outliers should be recognized and eliminated. Missing values should be spotted and either removed and imputed by proper methods. Data should be converted to proper formats. Generally, a data preparation step comes along with exploratory data analysis, which complements the overall preparation process. EDA helps engineers get familiar with the data they work with. It usually implies building some plots that can help with the data from different perspectives. Intuition that engineers get from such an analysis helps later on in finding the right methods and tools for data preparation, model architecture, algorithm selection, and of course, proper metrics choice. In case your work is in the supervised learning domain, you will need a label for each sample in your dataset. The process of assigning labels to data samples is called data annotation or data labeling. Data annotation is a manual operation which is pretty time-consuming and quite often performed by third parties. There's a rare case where machine learning engineers themselves work on labeling. Given the fact that you and your team will most probably not go over the annotation process by yourself, your main goal at this step is to design a comprehensive annotation guideline. The guidelines will let annotators know what to do. That's why it's crucially important to come up with a well-rounded guide that will cover the most essential aspects of the annotation job. Don't forget about the edge cases that might occur during labeling. Your annotation team should be prepared for every possible scenario they might face. There's no place for assuming in the annotation job. Everything has to be clear and transparent. You should also assign a person who will assist the annotations team. If you can't process a particular example, annotators should know who to contact to address their questions. Additionally, you should version your dataset and associate a given model with a dataset version. Tip: after labeling data and training an initial model, look at the observations with the largest error. These examples are often poorly labeled. In terms of setting up and tuning your model, start simple and gradually ramp up complexity. This typically involves using a simple model, but can also include starting with a simpler version of your task. Once a model runs, overfit a single batch of data. Don't use regularization yet, as we want to see if the unconstrained model has sufficient capacity to learn from the data. Survey the literature. Search for papers describing model architectures for similar problems and speak with other practitioners to see which approaches have been most successful in practice. Determine a state-of-the-art approach and use this as a baseline trained on your dataset. Reproduce a known result. If you're using a model which has been well studied, ensure that your model's performance on a commonly used dataset matches what is reported in the literature. Finally, understand how model performance scales with more data. Plot the model performance as a function of increasing dataset size for the baseline models that you've explored. Observe how each model's performance scales as you increase the amount of data used for training. Once you have a general idea of successful model architectures and approaches for your problem, you should now spend much more focused effort on squeezing out performance gains from the model. Build a scalable data pipeline. By this point, you've determined which types of data are necessary for your model, and you can now focus on engineering a performant pipeline. Apply the bias variance decomposition to determine next steps. Break down error into irreducible error, avoidable bias, variance, and validation set overfitting. Use coarse to fine random searches for hyperparameters. Start with a wide hyperparameter space initially and iteratively hone in on the highest performing region of the hyperparameter space. Perform targeted collection of data to address current failure modes. Develop a systematic method for analyzing errors of your current model. Categorize these errors, if possible, and collect additional data to better cover these cases. When evaluating your model, you should do so on the test distribution, as you need to understand how data in the wild is different than what you trained on. You should revisit the model evaluation metric and ensure that this metric drives desirable downstream user behavior. If you haven't already written tests for your code yet, you should write them at this point. Different components of a machine learning product to test include the following. Test the full training pipeline, from raw data to trained model, to ensure the changes haven't been made upstream with respect to how data from our application is stored. Run inference on the validation data that is already processed and ensure model score does not degrade with new model weights. You should also have a quick functionality test that runs on a few important examples so that you can quickly ensure that you haven't broken functionality during development. These tests are used as a sanity check as you are writing new code. Also consider scenarios that your model might encounter and develop tests to ensure new models still perform sufficiently. The test case is a scenario defined by the human and represented by a curated set of observations. This slide illustrates what we discussed previously. You can see that a plethora of tests are required to maintain smooth performance and minimize surprises. Also, the monitoring process breaks down into several components. When it comes to model deployment, be sure to have a versioning system in place for model parameters, model configuration, feature pipeline, training dataset, and validation dataset. A common way to deploy a model is to package the system into a Docker container and expose a REST API for inference. Two concepts to keep in mind: canarying, which is serving a new model to a small subset of users while still serving the existing model to the remainder. Check to make sure rollout is smooth, then deploy the new model to the rest of the users. And another concept, shadow mode, which is when shipping a new model alongside the existing model, still using the existing model for predictions, but storing the output for both models. Measuring the delta between the new and current model's predictions will give an indication for how drastically things will change when you switch to the new model. When it comes to maintenance, you should keep several things in mind. Machine learning systems are tightly coupled. Changes to the feature space, hyperparameters, learning rate, or any other knob can affect model performance. Mitigate this issue by creating model validation tests, which are run every time new code is pushed. Also decompose problems into isolated components where it makes sense to do so. If your model and/or its predictions are widely accessible, other components within your system may grow to depend on your model without your knowledge. Changes to the model, such as periodic retraining or redefining the output, may negatively affect those downstream components. To mitigate this scenario, control access to your model by making outside components request permission and signal the usage of your model. Avoid depending on input signals which may change over time. Some features are obtained by a table lookup, like word embeddings, or simply an input pipeline which is outside the scope of your codebase. When these external feature representations are changed, the model's performance can suffer. Mitigate this possibility by creating a version copy of your input signals to provide stability against changes in external input pipelines. These versioned inputs can be specified in a model's configuration file. Also, regularly evaluate the effect of removing individual features from a given model. A model's feature space should only contain relevant and important features for the given task. Finally, as the input distribution shifts, the model's performance will suffer. You should plan to periodically retrain your model such that it has always learned from recent real-world data. To sum up, a typical team is composed of a data engineer who builds the data ingestion pipelines, a machine learning engineer who trains and iterates models to perform the task, a software engineer, which is the person aiding with integrating machine learning models with the rest of the product, and finally a project manager, who is the main point of contact with the client.